We are in Generalized Linear Models with Examples in R, Chapter 1, Question 1.5, which is right here. Okay, so you can read it for yourself, but we are given several regressions, or something like regressions here, and they're all different in terms of their systematic component, which is what I'm highlighting here. Okay, and so for each one of these, we are supposed to say if that particular systematic component is linear in its parameters. We'll talk about what that means, and whether or not it is suitable for linear models, for generalized linear models, or both. Okay. So first, what does it mean to be linear in parameters? Okay. Well, so what are the parameters? First of all, the parameters are the betas. And why are they parameters? They're parameters because we need to estimate them given the data. Okay, now that differs from something like x or y, or in this case mu, where mu is the expected value of y. Okay, because we've actually measured x, we've actually measured y. Okay, and when we go through and we are trying to solve these equations, or more precisely, when our computer is solving these, it's estimating the betas, it's estimating the coefficients that will minimize some error given the data that we've measured, which is the y's and the x's. Okay, so things that we need to estimate are called parameters. That's what that's all about. Okay, so what does it mean to be linear in the parameters? Okay, well, if it's linear, then our systematic component will just simply be a sum of the coefficients, the parameters, okay, or the parameters as a product of the parameter and data. Okay, so that's what it means to be linear in this case. All right, so so in other words, what would be not linear? So not linear would be something like the coefficients, or the parameters, the beta coefficients are the parameters, somehow being multiple, interacting as multiples of one another. Okay, or maybe where an exponent or where a parameter is an exponent, or something like this. Okay, so this does not mean that these types of equations cannot be solved. They just cannot be solved with the same methods with which we use to solve linear models. Okay, so let's see. Last important point is, it is completely okay for the x variables, which again are not parameters, we've measured these. It's okay if the regression has the x variables multiplying one another, okay, or there's some function of x, right, like the log of x or something like that. So for a little bit of intuition as to y, okay, so imagine that we're trying to estimate the beta parameters here. Okay, so why is it okay if the data is somehow multiplied by one another? So let's say instead of beta x1, we had beta x1 times x2, right? Beta 1 times x1 times x2. Well, because the x1, x2 would still just be a number, right? But we're still trying to estimate the beta 1. But now look at the inverse situation, where we have beta 1, beta 2, and again, we're trying to estimate these given the constraints that are implied by the data. Okay, well, if I have x, I know what x is, and now I'm trying to find the two things that multiply to one another to make y. Well, I can do that in a lot of ways, right? Because if beta 0 is a little bit higher, then maybe beta 1 is a little bit lower. And if I take a slightly lower value of beta 1, then maybe I take or beta 0, then maybe I take a slightly higher value of beta 1. Right? So in other words, there's a lot of possible solutions when we have nonlinear terms in the parameters, okay? But there's hopefully one solution given when we have a linear model. Okay, so let's look at these. So here's our first model, okay? Now, is this linear or not? Yes, it is, okay? It's linear because we have each parameter only being multiplied by actual data, and then each one of those terms is just added to one another. Okay, so in this case, we see this logarithm here and we think, well, maybe that makes it nonlinear, but that's not the case, right? Because we are just taking the logarithm of data. And so again, that's just fine. We can still estimate beta 2 just fine, or we can estimate everything just fine, okay? So this is linear. And furthermore, it's suitable for both linear models and generalized linear models. The reason as to why will become clear in the next few examples here, so we'll come back to that. Okay, so now I'm going to skip 2 and come back to it. So let's instead go to 3 here, okay? And so we need to know, is this linear or, well, okay, first of all, is this linear? Well, we see that that we have the parameters in an exponent, okay? And so as it's written, it is not linear, okay? In fact, let me go down here, okay? However, we can transform this entire equation by taking the logarithm. If I take the log of both sides, well, now I get the log of mu is this thing. And this is linear, right? And so, so even though it doesn't look like it at first, this is linear because it can be written in a linear format, okay? Now, is this suitable for linear models, generalized linear models, or both, okay? Well, it is suitable for generalized linear models, okay, but not for linear models. Why? For normal linear models. Why? Well, the reason is because we had to do this transform. Okay? When we transformed everything, when we took the logarithm of everything, that means that we can no longer use just normal linear models. We're now using generalized linear models, right? Because we are having to transform something. Okay. Now let's go back to 2. We see that 2 is similarly formatted, right? We have beta 1 and beta 2 exponentiated here, okay? But this one is not linear, right? Why? Okay, well, because if we take the logarithm of both sides, well, we'll get the log of mu, and we'll get beta 1 plus beta 2x, but then we'll have the log of beta 0 here, right? Because we had to take the log of everything, right? So when we have the log of beta 0, well, that makes beta 0 nonlinear, right? So anyway, so we cannot, so this is not linear. Number 2 is not linear, and we can't use either linear models or generalized linear models for it, okay? Now, finally, we are on number 4, okay, right here, okay? So again, we see that that maybe it's not linear because we have the inverse of this thing, and it's not really clear, but we can just take the inverse of everything, okay? So if we take the inverse of everything, then we get 1 over mu is this linear function, right? So again, just like for number, 3, if we applied a transform, then we got this linear expression. And by virtue of the fact that we had to transform it, it's not suitable for linear models, but it is suitable for generalized linear models. Okay.